Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our new series called War Stories. In this week's show, we learn that you can't necessarily trust an instrument, even if it's name brand and has been reliable for decades. I know your time is precious, so let's get started. Recall that a war story is a memorable personal experience that we might learn from. We are guided by the saying that the smart person learns from their own mistakes, but the wise person learns from the mistakes of others. In this valve story, we learn three things. First is to check and recheck calibration. Second is you can't always trust instruments, a theme we will return to more than a few times again in this series. 3. Instruments that have moving parts can be destroyed by friction. This could be as simple as a pressure gauge, or as complicated as a servo valve, or even more complicated as a loading system such as used for nips and converting. A servo valve is a control component with an operator or computer-controlled electrical input and a pressure output. It is sometimes called a proportional valve. This is more than you will need to know to understand this story. The machine builder that I work for as a winder design engineer was as professional as they get. Nearly every control component and system had calibration curves that were pre-calculated, that were issued as part of the service manual. Also, in that service manual was how to check the calibration in the field. What happened is not only didn't the calculated and measured lay-on rolls zero and gains matched, they weren't repeatable. This was very odd because Beloit had used hundreds of these name brand components, and they were always mil-duty reliable. If the system didn't calibrate repeatably, that meant that some component or the test itself wasn't right. The easiest thing to do was to check the performance of the servo valve by manually moving the input and then using an installed pressure gauge to read the output. Ideally, the curve should be linear and have a sensible zero. In this case, the control input was a robust 4 to 20 milliamp current signal, so that at 4 milliamps you would get zero pressure out. However, as seen in this calibration plot, the results were nothing like linear or repeatable. In fact, the most notable deviation was that the outputs for increasing input were below theoretical, and the outputs for decreasing input were always above theoretical. Lack of repeatability, and particularly hysteresis, which is the offset of the load and unload curves, is not only common with elements that move, it is the norm. However, what is not normal here is that the deviation is quite noticeably large. So much so that the control curve is 3 to 5 steps, none of which will repeat on the next calibration. One way to think of this is like the electrons in a shell moving around the nucleus of an atom. You can never know where the electron is. You can only guess that it will tend to be near a specific orbit, or in this case, the ideal line, more than it is well away from that line. However, it can be just about anywhere in that band. This means that your lay-on roller will not load predictably, and your wound roll will be wound at different tightnesses, even though the inputs and the computer says things are the same. This story is about friction. It begins by noting that the calibration or performance is not repeatable. You will also observe that low pressures are not accessible and are not available. However, you need to take it one step further to determine if it is your test that is not repeatable or some component of the system that is not repeatable, and if so, which one is it? If it is the system, you need to measure and rank the uncertainty of the largest source of friction. There could be anywhere from 2 to 10 such sources in a loading system, for example. In our case, this story is about a brand new servo valve that is defective because the valve body clearances are too tight. As you should have guessed, this story is not just about servo valves per se. It is rather that, in general, you should not trust instruments until they are calibrated and rechecked on occasion. This story applies to pressure gauges, servo valves, dancers, and nip loading systems, and much, much more. I hope you've enjoyed this nip control story. Stay tuned for next week's show, where we will show how a lack of calibration failed to uncover a 2x error in nip loading, and is representative of at least a dozen other similar events in the winder world that I've personally been involved in. If you have a topic you would like to hear about, let me know in the comment section below. If you found any of these stories to be interesting or useful, please like and share and subscribe. See you next time.